So I'm going to talk today about what I think is a straightforward but important topic in pharmacoepidemiology, and one that has gotten a lot of interest and a lot of research from our group at McGill in Montreal, particularly by my colleague Sammy Suissa. And so it's nice to be able to talk about this here. It's this immortal time bias, and I'll define what this is and talk a little bit about what we can do about it, both when we're designing studies and later when we're analyzing studies to avoid problems. So immortal time, it turns out to be somewhat tricky to define. To find some definitions, because you can find several. I'm going to use these two. Alec Walker called it the experience of study subjects that is event-free by definition. And Sammy Suissa called it a span of time in the observation or follow-up period of a cohort during which the outcome under study could not have occurred. So this is basically follow-up time for a subject in a study where something we've done to the study or to the design of the study prevents them from having the outcome. This is just a simple schematic of an example where immortal time bias might occur, where a patient might be immortal. These are three people, A, B, and C. They're both followed in a study from some time zero. And we see person A is followed until this time point T, where they're exposed to some treatment. And after that, they're exposed going forward. So this might be a person who starts follow-up because of a disease here, followed along till here, they start taking a treatment, and they're followed from there on. Subject B maybe starts at time zero with the same disease diagnosis and then is followed along and is never treated. Subject C starts with the same disease diagnosis and then is lost to follow-up at time T star, which I put before time T where subject A was exposed. So it's very common in pharmacoepidemiologic studies to use an exposure definition that is ever exposed versus never exposed. So in this case, subject A was ever exposed to this treatment, and subjects B and C were never exposed. Simple, but causes a big problem, because look what happens with subject A. They're ever exposed, but in order to be exposed, they couldn't have had the event in this time window. Subject C was identical to subject A at this time point, and then we lost them. Subject A was, again, immortal through this time until they had the exposure because we listed them as ever exposed. So this time window here, where they couldn't have had the event. If they had had the event, they would have looked like this and they wouldn't have made it to be exposed. This window where they couldn't have had the event is immortal. They're unable to have the event in that time window. Whereas subject B, who was never exposed, counts his entire time window under the unexposed group. Subject C also counts as unexposed, even though, again, at this time point here, they all looked identical in that they all were diagnosed with the same disease. They were all followed over time until this time point, at which point one of them was lost, and then later one of them was exposed to the treatment. So if we use ever exposed versus never exposed, we're going to get subject A as exposed with this time as immortal, subject B as unexposed, and effectively this time here where they were at risk and could have had an event is counted against them, whereas this time is not counted against subject A. There's an obvious problem there, that is, subject A is protected against the event by the fact that their exposure was delayed. On the other hand, we might have said, okay, well, why don't we just exclude this time window? Why don't we say let's not count this, but then we have subjects B and C being followed from the time they had their disease initiation. Subject A will only start following from here, so he or she is at a different stage in their disease process. So this should start to sound like a problem. Either A is protected against events here, or we're following them up at different times and creating a potential sort of imbalance. I'm going to frame this now in a couple of examples, and I hope this will help solidify the question. First one is, this is a famous study of heart transplant. So subjects were entering a study at the time they were put on a wait list to get a heart transplant. If they died while they were on the waiting list, that is assigned to not getting a transplant because they died while they were on the waiting list. The deaths that happened after a transplant were assigned to the transplant. The problem is, if I go back one or two, this is what's going on here. Subject A was followed along, they got a transplant here, and we only started counting events in that person here. Subject B, who never got a transplant, we could start counting events right here. And subject C, same thing. So the problem arises that only the healthiest patients are going to survive to get the transplant, and that first follow-up period where they can't have the event is counted in favor of the transplant, in favor of the treatment. So the bias there there's a bias that's going to favor the transplant or the treatment. This is now a famous paper from Sami Suisa talking about observational pharmacoepidemiology, where he found 20 studies, all of which showed what he thought to be implausible protective effects of medication. So these are medications being taken for some other thing, and they're showing reductions, big reductions in some other outcomes. So maybe as much as a 50% reduction in outcomes that they were not initially prescribed for. And he pointed out that all of these 20 studies either had misclassified immortal time or excluded immortal time. And this is the same schematic as before, but now pointing out with the drugs, with a drug setting. If we had misclassified immortal time, that is, a subject is exposed at diagnosis, then there's their first drug use, and then they die, versus the other subject who's unexposed, who we start counting time right from diagnosis. This time here, even though the person wasn't on the drug, is assigned to the drug, and it's impossible for them to have an event in that time window because we're only counting them as a user once they hit this drug event. If they had an event in this window, they would have been classified down here as unexposed. The other possibility was excluding immortal time, as I mentioned on the other side. When subjects were exposed, this was taken out, so you were following people from here versus from here. So these are people who have survived this amount of time with the disease, and then we start their follow-up going forward, versus unexposed, where we're starting right from the disease entry. Sami reanalyzed one problem and showed that if we treated things correctly, and I'm going to talk a little bit about how to treat things correctly in later slides, we can eliminate the bias. So this suggests, and this was just over 10 years ago, but it's still an issue in the pharmacoepidemiology literature, that immortal time bias can be a significant problem in pharmacoepidemiology work. So another problem is, another place where this can occur is in the study of pregnancy. So pregnancy is a very short 9-month time window, and babies that are born earlier in pregnancy, those are ones at higher risk for various side effects. In particular, if we're studying, we often study preterm birth as an outcome, and that's by definition a shorter time of pregnancy. So you have less chance to be exposed to drugs during pregnancy if you're born preterm. If we think about a drug that's given at an acute period during pregnancy, so not something that's given across the pregnancy, but something that's given at a specific time point, like a decongestant or a flu vaccine or some other point treatment, immortal time bias is at least a potential to occur if we treat the exposure as time fixed. That is, if we treat the exposure as ever exposed versus never exposed, because those pregnancies that go on for longer are the ones that are most likely to be exposed to the treatment. Or if we treat the outcome as time fixed, if we just say preterm versus no preterm, well, the preterms have a shorter time window to be exposed to the exposure than the term ones. So we create an association between the exposure and the outcome by mixing up the time axis when we're thinking about a pregnancy problem. Another one of my colleagues, Jennifer Hutchin, pointed out that this occurs with other risk factors for stillbirth as well, or pregnancy outcomes as well. She looked at risk factors for stillbirth and gestational diabetes, or gestational diabetes mellitus, or GDM, which is typically diagnosed at 24 to 26 weeks of pregnancy. If the non-GDM cases, that is the people who don't have gestational diabetes, are followed from 20 weeks, well then that time window for the GDM cases between 20 and 24 weeks is immortal, because you can't be diagnosed in that time window, and so it fits that same graph that I started with earlier, where you can't be exposed in that early window, and if we're going to count you as ever exposed versus never exposed, all those early events are going to be assigned to the unexposed group. So in this case, all of the stillbirths that occur in weeks 20 to 24, before you could be assigned to be a gestational diabetes pregnancy, were assigned to the non-GDM group, and therefore the GDM, the exposure, looks to be protective against stillbirth. And this is a complicated graph, but we can ignore all of the text alongside the graph here, but this one illustrates nicely the problem. So this is now kidney transplant patients, and time zero here is when they start dialysis, and these have been ordered in terms of the length of follow-up. So this patient was followed only for a couple months. This is 1 year, 2 years, up to about 9 years of follow-up. You can't quite see this here well, but some of these time paths have a flat line at the end. That's a death. Some have a pointed line at the end. That's a loss to follow-up or a censoring. And we see what happens here is, and then the next thing about this is, where a subject changes from black to red, that's a patient who was on dialysis until this point and then was given a transplant, and then were followed to, in this case, a censoring event. This illustrates the same kind of problem as the heart transplant problem that we had earlier. These patients here who died very early or were censored very early, they really had no chance of being followed long enough to get a transplant, whereas these patients down at the bottom who have longer follow-up have a much likelier chance of getting a transplant, like these two here, for example, who had long follow-up off transplant and then were put onto transplant. If we then treat this as ever exposed to transplant versus never exposed to transplant, all this time here for this patient and all this time here for this patient are treated as being assigned to the transplant group, even though they were not being transplanted at that time. Or they were not under transplant at that time. And if this person here here and classified them as an unexposed. So they're exposed, and their time before they were exposed is immortal, because if they had an event there, they would have been classified as unexposed. Okay, so this graph nicely illustrates, I think, the potential problem here. This is another one of my McGill colleagues, Jim Hanley, who had the idea to describe this way. So this brings us now to sort of a summary of when does immortal time bias occur. So was treatment status determined after the start of follow-up time or defined using follow-up time? Either of these cases potentially could give rise to immortal time. Was the startup time of follow-up different for the treated and the untreated or comparator group relative to the date of diagnosis? This should be the real red flag here for that exclusion of immortal time, where here we're taking the immortal time and leaving it out of our study. Were the treatment groups defined and identified hierarchically? Did we identify one group after the other, before the other? So did we identify ever exposure and then say, is anybody else left? You guys are the unexposed. Were subjects excluded on the basis of treatment identified during the follow-up? So were people thrown out of the study? I didn't show an example of this, but were people excluded on the basis of a treatment change that was identified during the follow-up? And or was a time-fixed analysis used? Did we say ever exposed versus never exposed? All of these examples here, or these conditions here, have sort of a common theme of an exposed group and an unexposed group where we're misaligning something about the time axis. Either we're taking that period of immortal time and assigning it, even though it's unexposed time, to an exposed group, or we're excluding it, or we're excluding subjects based on something that happens after time zero. We're misaligning the time axes between the exposed and the unexposed groups in a systematic way that causes potential problems. Okay, so we've identified that there are potential problems with immortal time bias, and that they have to do with this misalignment of the time axes. So I'm going to talk now for the rest of the session about what we can do about it. First of all, I want to talk about how we can prevent it, and there's a lot of natural design-based ways to prevent immortal time bias, or to make sure that it's not a problem. Okay, I want to now think just for a second about these three times here. Time where we determine whether somebody is eligible for a study. That's typically the date of diagnosis with the disease, say. We think about treatment strategy assignment, or the decision to treat or not, or to treat with something versus something else. And time zero, that is the start of follow-up for a subject. So if we think about a randomized trial, then in a randomized trial, all three of these things are the same, because, or unless we're talking, and we may modify time zero here, but for a simple randomized trial, they're all the same. We determine that you're eligible, we randomize you to exposed or unexposed, and then we start following for events. And it's straightforward. We structurally eliminate that problem where the follow-up times may be misaligned between the exposed and the unexposed in a systematic way. That's a randomized trial. We're doing an observational study here. Or most of the time we're in pharmacoepidemiology, we're doing observational studies. How do we get to use that kind of thinking about a trial in an observational setting? And Miguel Hernan from Harvard has written a number of papers talking about what he says emulating a target trial. So the idea here is to say, okay, we're doing an observational study, but what would it have looked like if we were doing a trial, and how would we best take our observational study and make it look like a trial, and therefore design it like a trial. And this reference here, we worked on talking about immortal time in the context of this target trial idea. So showing that thinking about these 3 time points in an observational study and trying to align them as if we were doing a randomized trial essentially eliminates immortal time. And I'll go into that a little bit on the next couple of slides. So this is another similar schematic. Subject A and B are diagnosed with their disease on the same day. Subject A is followed until initiating a treatment right here, and then they're followed forward from treatment initiation. Subject B is followed from diagnosis until treatment initiation, except he or she didn't initiate the treatment, and then he or she is followed after that. The idea or the principle that we want to put forward here is think about this like it were a randomized trial. And if we think about, okay, A was randomized, in quotes, into treatment at this time here, then B should have been randomized into no treatment at this time here and followed forward from here. So if we think about our randomized trial as starting here, and it's simple, we only count the person time for person A going forward from here, we identify person B here, and we follow them forward in time. There. I'm going to talk a little bit. There's a little bit of a tricky spot about how do we identify this point here for person B, and we'll have some ways around that on the next couple of slides. But we could also have said, okay, what if we said randomize them at diagnosis? Even though they're both untreated here, we could have randomized A to say, okay, I'm going to follow you from here and then treat you here. And I'm going to follow B from here and not treat you there. If we were doing that as in a randomized trial framework, we would think of these as treatment strategies. They're not, this is one treatment strategy to say delay your treatment until this time point. This is a second treatment strategy to say never treat. And we would have randomized the 2 different strategies, and any event that people who look like A have in this window would be assigned to that, in a somewhat paradoxical way, to that treatment strategy of delay treatment for a year but then start treatment. That gets around immortal time bias. It changes the question to something a little different, which we can spend some time on in the questions if people are interested in, or you can refer back to the paper I referenced as well. But it can be set up that way as in a way that won't create the bias, as long as we say treat the people who are at time 0 in both possible groups identically. So we identify the treated in our exposed group and the time at which the treatment exposure was initiated, and we try to identify subjects who are untreated at the same time. So if I think about that for a second, identifying subjects who are untreated at the same time as somebody who is treated might be tricky because, for example, if I skip back a slide, this person here was followed from diagnosis to here. We know that this person was in a doctor's office on this day in order to get a prescription for the treatment. Person B might have had a diagnosis on the same day and then disappeared. We might not know that whether they were in the doctor's office to get treated or not. So we might not have a natural way of identifying the untreated subject at this time point. So this is one way around this, and one way that's been talked about a fair bit in the literature is using an active comparator. So for example, in some of our studies in the Canadian Network for Observational Drug Effect Studies, we use active comparators. So we're saying compare high-dose statins to low-dose statins rather than statin to no statin, because we know that we can think about somebody who was exposed to a low-dose statin on the same day as the high-dose statin, and we know that they were both in the doctor's office potentially getting a prescription on the same day. And then, as I mentioned earlier, if we start a diagnosis, we have to think about treatment regimes. We have to think about these treatment patterns of start treatment a year from now or start treatment 6 months from now, and things get considerably more complicated. So I mentioned this already, but I'll come back to this, what I think is an important point, the idea of an active control new user design. If we create our target randomized trial, so again, taking our observational study and mapping it back to what it would look like if it were a randomized trial, if we first say, okay, I'm only going to start with new users, and so that means I'm always looking for events where people are initiating treatment, and I'm starting to follow up from that point. I've got those time points where my eligibility for the study, my follow-up time, and my treatment time are all aligned. That works well. The second part of it, to make sure I'm thinking about it like it's a trial, is the active control. That is, I'm going to think about saying, rather than look at treatment versus no treatment, if I look at treatment with A versus treatment with B, or treatment with high dose versus low dose statins, I know that I can identify the time at which the decision was made to treat with A or treat with B. And so, by using this active control new user design, I've sort of set things up to mimic the randomized trial a little better than I would have if I was thinking about treatment or if I was thinking about prevalent users, because it's harder to identify that time to zero. Now, a relatively recent development in the design literature is this prevalent new user design, or it's also been referred to as the treatment decision design. Sometimes you can take users who are prevalent users and identify a decision point where some switch to a new drug and some don't, and think about that as, again, mapping back to a target trial. And if we think always about making sure that the time points all line up, we're going to be able to prevent immortal time bias from occurring. So that's our design approaches. And again, they all revolve around this idea of thinking about our study like it's a trial, or like it would have been a trial, and what it would have looked like under those settings. So at the analysis stage, let's say now we have our time-varying exposure, and we know that there's immortal time in our study if we treat it as exposed versus unexposed. The simplest thing to do, and this goes back to relatively old literature in the case control literature, is to simply assign the person time to the same exposure category that an event would have been assigned to were it to occur at the same time. So that's a long sentence, but it's actually relatively simple, and I apologize for skipping back the slides here, but I need my graph again. All this is saying is, if I treat patient A as unexposed in this time window and then exposed going forward, and I treat patient B as unexposed the whole time, and I treat now patient A's exposure as a time-varying exposure for unexposed and then exposed, then if he or she were to have an event in this window, they would be classified as unexposed and not exposed, and it would get rid of the potential immortal time bias problem. So in the transplant study, everybody who's assigned to, actually, I'm going to skip ahead to the observational pharmacoepi example. In observational pharmacoepi, if we assign the unexposed time window to non-treatment, and then do time-varying analyses with either a time-varying Cox model or a nested case control design, then we're okay. In the transplant trial, if we assign the person time to the same exposure category that event would be assigned to where it occurred at the same time, if we assign that unexposed time window to non-exposed, then it's fine. If we assign that unexposed time window to exposed, but say, okay, those are people who will eventually get a transplant, then if we know that those patients will eventually get a transplant, we can count them as exposed. That's a little confusing, so perhaps we can come back to that, I think, in a bit. Okay, so a little bit more detail on the analyses. I mentioned you could use an as-treated nested case control design. If you sample from the risk sets, so cases plus at-risk controls, and use exposure at the time of the event, you're always getting you're always getting whatever exposure the patient was on at the time the event occurred, and you're comparing to controls who have a similar history but didn't have the event, and so we get a legitimate comparison of people who are in the same state. If we think there's constant risk, we can reduce this as treated result to a piecewise Poisson model, which is a little bit simpler, but not necessarily more useful. Or we could use a time-varying exposure and a Cox model and fit a Cox model with time-varying covariance. This is the computationally and technically most complicated, but it takes into account what we want from those time windows. If you have an unexposed time window, it's counted as unexposed. If you have an exposed time window, it's counted as exposed. It might be required if we have a time-varying exposure, where a time-varying exposure is affected by a confounder, and the confounder is affected by earlier exposure, to think about things like marginal structural models or other related methods that take into account this kind of time-varying structure, because then we know that the exposure may be affected by things that change over time that may then bias the results. That's probably for another lecture, but we'll leave that there so we know that it's a potential problem. The final analytic option that we might think about is something called the landmark method, and this is a little bit like that active control new user design. We sort of set an arbitrary time point that we call a landmark. We measure exposure prior to that time, so that if before that time you were exposed, you're counted as exposed. If before that time you were not exposed, you're counted as unexposed. We ignore and censor events that happen prior to the landmark, and then we follow events after the landmark. So this is a little bit like a new user design in theory, and it has this sort of target trial flavor to it, just by saying we'll set an arbitrary time point that we'll call the landmark time, and we'll treat the randomization, in quotes, as occurring there, and so the target trial, it looks a little bit like a randomized trial. So, immortal time, and if you read the pharmacoepidemiology literature now, it's been talked about in the literature for 10 or 15 years. It dates back to the 1970s overall. In the statistics literature, it's still a significant problem, but it's relatively easily avoided. The easiest way to avoid it is to think of it as a design problem and to use design solutions by clearly identifying time zero, counting all events and assigning them to the correct exposure group, by mapping observational studies to well-defined target trials so that we know we're lining up exposed and unexposed, we're lining up time zero in the two groups, and that'll minimize the problem. And then, failing that, we can still fall back on our analytic solutions, in particular either the nested case control design or the Cox model with time-varying covariance, in order to adjust for the potential immortal time bias. So I hope these slides are being made available to you guys, because you won't be able to read these. I will only point out just a little bit of advertising. We have a new review coming out in Current Epidemiology Reports on immortal time bias. I believe it's either just about to be published or it's just been published. Sort of giving an overview of the things I talked about today and the target trial approach to avoiding the problem. With that, I will end there and take questions if there are any.
Thanks, Rob. That's great. Question, if I may. The place that immortal time bothers me most is in compliance studies. And so what we do is we look forward to decide if you're compliant or non-compliant. And then, for me, the question of time-varying analysis doesn't seem to work in that, I don't think, because then you're going to compare full use with no use, time-varying stuff. So the only method I can think of is to assign compliance and then look forward and assume that future compliance is going to be like your last compliance. But if you have another solution, I'd be really grateful to hear it. Thank you.
Yeah, that is a challenging problem that I don't know that I have a good answer to either. And that's usually why, if I put my statistician hat on and fall back on randomized trials, we'll think about ITT because compliance is too hard to think about. I think the methods that Hernan and his colleagues have published on recently, where they're trying to address what would happen if everybody complied versus what would happen if nobody complied, are helpful, but they do kind of set up, like you said, a somewhat artificial situation. The other approach that also kind of sets up a problematic situation that has gotten a lot of use in the compliance literature is the principal stratification, where you try to identify a group that say, okay, this is the group that would comply if they were in the exposure versus the unexposed group. And then we can sort of estimate what the effect is in them. The problem is we can't identify whether you're going to be in that group or not. And so it's not that useful when you're faced with a patient. You can say to the patient, if you think you're going to be in this group, then you should, but we don't know that really what that's going to be like. So there isn't really a good solution to that problem.
And sort of related to that, when you're looking at discontinuation and persistence as well, quite often you're looking forward 30 days or so to see whether they stop using. I was just wondering how model time bias will play into that, if people die within that period, and how you control for that.
So you're looking forward to deciding. So
usually, if someone discontinues a drug, you have the last net they use, and then there's a period of time where someone doesn't use. They arbitrarily or clinically decide. So 30 days or 60 days of no use, that means they've discontinued at that day. If someone dies in that period, do they die as a continuous user, or they die as a discontinued user?
Yeah, I think. I mean, it seems like a cop-out to say this, but if you fall back sort of on an intent to treat idea and say, okay, think of them as worst case they would have been a continuous user in that setting, then you're at least not looking into the future with them. I think you probably could, if you thought about a nice way of thinking about that as a sensoring mechanism and accounting for it appropriately, you'd probably get a better answer under more assumptions, but I probably would fall back on an ITT just because it's the safest, I think.
Thank you for a very nice presentation. What I have is more of a comment than a question. You mentioned the use of nested case control studies as a solution. I fully agree. I tried once to build an immortal time bias in the nested case control study. You can mimic any cohort study in a case control study, even a flawed one with immortal time bias in it. And what I had to build was so peculiar that I did not possibly have done it by mistake. It was delivered to illustrate a methods problem. It would require you, for example, to include observation after the index date, something that you would normally never do.
Right.
Think of case control studies as a good way to avoid.
Yeah, I think the nested case control is probably the or a simpler way to avoid immortal time. I hadn't thought about what you just said, but that's plausible that it's hard to construct a nested case control where you're forced to have immortal time. You really must have to create a pathological situation. So this afternoon we are moderator free, so it's my pleasure to introduce the next speaker. We're going to go in order. The next speaker is Darren Toe, who is on faculty at Harvard and is one of the lead investigators for the Sentinel group at Harvard. He's going to be talking about distributed networks. Right?
Good afternoon. My name is Darren Toe. So I'm going to talk about this topic. disclosure. The work that I'm going to present was or is funded by some of the funding agencies here, so these are all in the United States. So this is an overview for the time that we have today. So I'm going to talk about the need for multi-center study. So if you don't do multi-center study, you can zoom out or just think about something else for the next 40 minutes. And then I'm going to talk about analysis that uses pool individual level data analysis. And the third is to talk about methods that you can consider if you are not able to share patient level data and have to rely on summary level data. And then I will talk about additional considerations that apply to both type of data sharing. And then spend some time talking about whether you actually need to have a common data model in a multi-center study, and then end with some discussion. Multi-center studies. I actually don't know how many of you are doing or are thinking about doing multi-center studies, but there are actually multiple multi-data-based studies. A lot of them are in what people call a distributed data network structure. So Robert mentioned C-nodes, which is, sorry about this. C-nodes, yeah, which is here, which is a collaboration in Canada. And we have a counterpart called Sentinel in the US, and there are also other networks in the US or in the Asia Pacific network. So there is a pharmacoepidemiology network called Aspen. So why do we need a multi-center study? Usually that means that one database is not sufficient to answer your questions. Maybe because you want to look at rare exposure or rare outcomes, or you want to look at very specific subpopulation. Sometimes you want to do the study more quickly. So instead of waiting for 3 years in one database, if you're able to bring together multiple databases, you'll be able to accumulate the sample size much faster. And that's usually the situation in which you might want to study a new medical product when it reaches the market. So by having more databases, you'll be able to get the study done more quickly. And the other big categories is that you might want to get a more diverse population. So maybe the database you have only has certain demographic. So you might want to have a more diverse population by bringing together different data sources. So this is multi-center study version 1, which is still very commonly used approach in that you ask each data contributing site to create an analytic data set, and then you just pull the data set together to create a gigantic pool individual level data set. So the type of analytic methods you can consider with this type of pool individual level data set is exactly the same as in your own single database study, because when you pull all the databases together, it essentially becomes a larger pool individual level data set. So the methods that you're going to use will almost exactly be the same. So I tend to think about these 4 domains. It's actually not in sequence, and I'm going to explain to you what I mean. So you can think of the covariance summarization technique. So we are mostly talking about observational studies in which you have to adjust for a large number of biases by measuring the covariance and accounting for them in the analysis. And then once you figure out this, you think about how do you share the information, and then the type of analysis you can do. And actually this usually comes first. You have to think about the research question before you think about all the other things, but it's just easier for me to draw the graph this way. So I try to think about it in a simpler way, is what to share in a multi-database study, how to share the information, and what can you do with the information that you share, what type of outcome can you study. So if you have a pool individual level data set, if you think about these 4 domains, it actually is a pretty straightforward exercise. So this is the typical data set that you share in a multi-center study. So most of us do analysis, so this is an easier way for me to just talk about this in a more common language. So in the study, each observation or each row is a person, most of the time, if you are doing a simple analysis. And each column is a covariate that you need for the analysis. So if you're talking about an observational study in an electronic healthcare databases, you might be talking about a database with hundreds of thousands of rows and maybe up to 100 columns, because you need to account for a lot of confounders, and you measure them and So I say this, I say this. And this is just how you combine them in a more visual way. So essentially, after pooling, the structure looks exactly the same as you. Usually, we would create a site indicator because you will want to account for site in your analysis. We are going to talk about it in a minute. So if you apply this now for domains, think about the data structure we just saw. And think about this, the covariance summarization technique, you decided that you shade individual covariance, which is the columns that we just saw. And then the data sharing approach is you shade individual level data. And then you talk about the adjustment techniques. So these are the most commonly used techniques in observational research. You can do matching, stratification, restriction, weighting, or modeling. And the type of outcome, if we are not talking about repeated or time-varying outcomes, we are mostly talking about continuous binary count and survival outcomes. So we usually use linear regression, for example, for this. This is logistic regression, this is Poisson, this is cost regression. So if you share patient level data, this will be end of the presentation because you can do pretty much whatever you want because you have all the data that you need. So you can, again, zoom out, not listening to the next section until we come back to the additional consideration section. But they are often concerned about sharing patient level data. This is true definitely for the work that we do in the US for these reasons. You might have your own challenges. So there are concerns about patient privacy. There are actually also a lot of concern about institutional privacy. And then people like us, epidemiologists or biostatisticians, are sometimes worried about inaccurate analysis or interpretation of the data. Sometimes we are worried about sending people our data and then they do whatever they want with our data and not telling us, and then you find out after they publish the paper. And that doesn't always happen, so it's more like a perceived concern, but it does happen sometimes. And then there are some contractual restrictions or legal restrictions that forbid people from sharing data with you, even if they want to. So there are considerations that they have to think about before they can share data with you or with us. So we have to come up with other solutions to do the analysis that we want without sharing patient level data. So this is actually a pretty delicate balance you have to achieve. You need to be able to do the analysis that you wanted, but at the same time you need to think about the type of information that people can or are willing to share with you. So this is what we call multi-center study 2.0. So instead of sharing patient level data, try to share aggregate level information so that the patient information is not identifiable. And if you're also able to mask the institutional level information, that will be even better, especially for some of the delivery systems that we work with or the health plan or insurance companies that we work with, because sometimes there's proprietary information they would rather not share. So this is where we talk about how one can do analysis without using patient level data. So the three big categories that we are going to talk about are listed here. So the first one is something that actually we use in pharmacology quite often, which is based on summary scores. So we are talking about scores like propensity scores or disease risk scores. So they have very good properties that we can sort of leverage for multi-center study that you are going to see later. And then the second is actually a pretty straightforward exercise. You just ask everyone to do his own study and you try to combine them using meta-analysis. And then the third one, which I personally think is a very cool method, but the biostatisticians don't necessarily think so. So you can be the judge after we describe this method later. It's called distributed regression. So propensity score, many of you have heard of it or are using this type of score in your research. The two major or most commonly used scores are propensity scores and disease risk scores. So this is just a very simplified version of how they handle the confounding triangle that we are all trying to think about all the time. So propensity scores, like what is shown here, is the probability of getting the treatment of interest given the measured baseline confounders, and disease risk score is modeling the associations between the confounders and the outcome. And the nice thing about these scores is that if you do it right, you'll be able to condense the information from a large number of individual covariates into a single score that in itself is not identifiable. So what we mean is that if I tell you that my propensity score is 0.29, if I don't tell you anything else, you wouldn't know anything about me. You wouldn't know how old I am, you wouldn't know my sex, you wouldn't know my medical history. But if you do the propensity score modeling correctly, this 0.29 score would contain all the information that you need to adjust for the confounding factors that are used to estimate the score. So that is a nice property of propensity score that you can sort of leverage in your multi-center study. So if we think about this in the data structure format again, instead of sharing this sort of very wide data, you can summarize it with just one variable. So you sort of reduce your data dimension by quite a bit. But this ultimately is still individual level data. And remember that some people or some data partners are not able to share patient level data. So this is just getting us halfway through to what we want to get to ultimately. So if you're being creative, you can combine propensity score or disease score with other methods. So for example, if you decide that matching, propensity score matching is a reasonable method, then you can further process the data before you do analysis. So for example, if you are able to do propensity score estimation in each database and then do the matching within each database, and then you think that, okay, I can just do some sort of Poisson type of analysis. All you needed, assuming that matching is done well, meaning that there are no imbalances after matching, these are the 4 numbers that you need from each data source to do your analysis. And we have paper to show you under certain assumption, you will get results that are identical from the analysis that you will get from a pool individual level data analysis. So instead of combining a large data set, you just need to combine 4 numbers from each side, and then you can do your analysis. The next approach is that you can do stratification. It's actually the same concept. Within each stratum, you share the same 4 numbers, and then you ask the data partner to share this summary level data set, and then you do the combined analysis. The third one is trickier to explain. It usually applies to time to event analysis. So you sort of restructure the data into what people call a risk set format. So if you remember the risk set is created whenever there is an outcome event, and then you look at the study population to see who else is at risk for the outcome. So people have shown that if you restructure your data into risk set, so this is just one type of data structure that you can create. You create a row every time there is an event, and you sort of get information about the event time, and then look for the exposure status of the person who had an event, and then look at how many people within the risk set are still exposed or non-exposed. And people have also shown that by creating this type of data structure and feeding a specific type of model, you'll be able to get results that are mathematically identical to a stratified Cox model. We are going to show some empirical data to support this later. So meta-analysis is as simple as it can be in that you just treat each database as a study and then ask the data partner to do the analysis and get an effect estimate. And this is the most summarized, the least granular type of information you can share in a given study, because you only need to share the final result and some sort of confidence interval or variance that will allow you to create a weight, which means the contribution of each database. So this is where the epidemiologists and biostatisticians disagree. So this is a distributed regression method. The reason why they disagree is that for biostatisticians, this is such a simple concept, they couldn't understand why we are still talking about it. But for the epidemiologists, this sounds like a sort of black magic. I still think it's a black magic, and I'm going to explain to you why. So this is what you typically input in in an analysis to a statistical software. So let's say you're using SAS or R. You are imputing a patient-level data. So it can be a full patient-level data set, or it can be just a single database. You don't see what goes behind the scene. What you see is what I show you on the right-hand side, which is the final results. So there's a lot of stuff that is going on when you run prop PHREF, for example. This is in SAS language. Actually, SAS, or the statistical software, or actually the model feeding process, will create a bunch of stuff that is not recognizable. So this is what we call intermediate statistics or sufficient statistics, or some sort of spread cross-product metrics. So it actually contains the same information as the patient-level data. But as I show you, so these are sort of from a real study. It's highly summarized. It's not recognizable, and the goal is that if it is not recognizable, it's useful for multi-center study because you don't want your data to be identifiable. So this is what regular regression shares. This is what distributed regression shares. So if you're able to process the data from patient level data to this type of summary level data, you'll be able to do the analysis exactly as what the patient level data can do. So this method has very nice property in theory because it follows the same computation process. So if you do it well, you should be able to get results that are identical to what you're going to get if you pull the data together. So I'm going to show you some examples to show you that I'm not making this up. So this is the first example that is sort of comparing the summary score-based methods. So we did a study looking at two surgery types for obesity. So this is the gastric banding procedure and gastric bypass procedure. So the critical context is less important for us. The numbers are more important for us for our discussion. So we did a very traditional quote-unquote new user design, meaning that we identify patients who had incident surgery based on certain washout criteria, and then we follow them until the outcome event, which is the hospitalization and one of the sensory events. So very typical new user design. So for this observational study, we consider more than 20 covariates. And we decided that we would use propensity score to summarize the covariates because it was just a reasonable method for us to consider in this context. And we were very lucky that we were able to ask the data partner to share patient-level data with us. So we actually have a very good benchmark. So everything that the summary level data analysis are trying to do is to get as close to what the patient-level data analysis can do. So it serves as a very good benchmark. So if the results are similar or identical, then you can argue that you don't actually need to share patient-level data. You can share summary-level information. So we did a reset-based analysis, we did a perpetual stratified analysis, and we also did the meta-analysis. So these are the results by site. So in total, there are 7 sites who contributed to the analysis. So these are the adjusted hazard ratio. So this is comparing the two procedures and their risk for hospitalization after the patient was discharged. So these are the results. So to orient you, so this result is from the pool individual level data analysis. It serves as a benchmark against which these 3 methods are compared. So this is presenting the data in figure. These are the actual numerical value. So as we just talked about the risk set approach, in theory, should give you identical result, and this is what we were able to get from the study as well. And the perpetual stratified analysis and meta-analysis give you sort of comparable results, but not identical. But for most purposes, you probably think that the results are close enough. So this is the second example that we did for distributed regression. So we sort of downloaded the data that was publicly available, and then we repeated this analysis. So the method was developed by Alan Carr and Steve Feinberg. So these are statisticians and computer scientists that had the same situation of not being able to get patient-level data in the study. So they did some work, and then they made the data available, so we repeated their analysis. So this is what you need to share, as we just talked about for distributed regression. Instead of sharing patient-level data, you sort of process the patient-level data into these highly summarized sort of numbers that you don't actually recognize. And the goal is that you are not able to recognize the numbers. So the three sides share this type of information. And then we're able to replicate the results. So this is what we get from combining the 506 patients' data and do a pool patient-level data analysis. This is from RAC in SAS. This is from distributed linear regression. So there is no standard software that allows you to do that. So we have to create our own SAS code to do the distributed regression. So using our favorite eyeballing approach, you see that the numbers are identical. So this is true for the parameter estimate, for the standard error, and by extension, all the statistical tests that you are going to do with these two numbers. This is from prop logistic. So this is the logistic regression with binary outcome. And again, the numbers are exactly the same as what you expect from theory. And this from the time to analysis. And again, the numbers are identical. So if you don't trust me, we actually did another study. So before I do that, I'm just going to show you that it's also possible to do some sort of model diagnostics using summary level information. It's harder to do it for a lot of reasons. So this is what we did just to get the error under the RC curve. So the number that you get from individual level data is 0.8255. And what we got from distributed logistic regression was close to the actual number, but not exactly the same. This is because if you want to create the area under the RC curve, you actually have to plot the individual data point to get the curve and the sort of associated C statistic. So if you want to do this without patient level data, you have to bin the data, so you have to sort of make them into categories. So this is from the bin of 6. So each group has 6 people. So if you have a bin of 1, then this will be identical. And the third study that we did was this. So I apologize for the color of the font. So we used another data set. We actually used a real data set from Sentinel to do this work. So this is from linear regression. This is from logistic regression. This is from COG model. The variables themselves are not actually the focus of this slide. This is the focus of the slide. If you compare the result from distributed regression and from pooled patient level data, you will see that they are exactly the same up to 10 or further decimal place, meaning that they are within machine precision. That's again what you would predict from theory, and you'll be able to prove that using real data. So here are the additional considerations. So I didn't talk about some of the challenges that you might face by applying some of these methods. If we have time later, we can talk about that. But I want to get to the other points that we always think about when we do a multi-center study. So the first is something I cannot emphasize enough, which is to account for data source in all the analysis. So we mentioned that estimating propensity by side, and if you do matching or stratification, try to also do that by side. So in the analysis, you can stratify on side, and you can adjust for side in the regression model. Just try to account for sides in your analysis. It gets to this other point, which is that sometimes there is extreme heterogeneity by data source. So it's always a good exercise to not only get the pool estimate, but also get the estimate by side. So I will not talk about this more because there's actually a symposium later in this conference. They will talk about how different multi-center collaboratives are doing to try to minimize heterogeneity or try to sort of measure or present heterogeneity. So what I did not mention is that the databases that you might be working with can be very heterogeneous in that some data sources have richer data, some have more missing data or more limited data. So in terms of missing data, it's always a good exercise to think about what people have done in single database setting and try to apply these proven methods in multi-database environment. The more commonly used methods are multiple imputation, inverse priority weighting. It's easier to do this type of methods if you can pull the patient level data. If you are thinking about only using summary level information to apply these methods, there are some challenges that you have to think about. It is possible under certain situations to borrow information from a data source with more information to help with the missing data in another data source. Again, we don't have time to go over that, but there's some work that has been starting to think about how to leverage information within the multi-center study to help each other out. So we get this question a lot, mostly from the reviewers of the journal. Is that, let's say different data sources have different data, variables. Do you go with one confounding adjustment or regression model, or do you allow each data source to fit its own model and then you do a pool analysis in some way? So having a common set of covariance across all the sites give you consistency. But other people argue that if a site had BMI, for example, but another site doesn't have BMI, so if you believe that BMI is a defect, you should ask the other site to adjust for BMI, even though there are some sites don't have the information. So we see argument both ways. And as epidemiologists, we like sensitivity analysis, so we always recommend people to do both. But you have to specify which one is your primary. So this final part is about common data model and non-common data model. So common data model basically means that you sort of standardize the different data sources into the common structure, meaning that you have a set of standardized tables and variables that are defined in the same way. So even though all the databases start differently, in the end, after this common data model conversion, they will look exactly the same. So there are actually some consideration you have to think through to see whether you need a common data model or not. But in theory, the methods we just talked about should apply with or without common data model, because common data model is just another way to sort of structure your data. So the methods that we are talking about in the past 20 or 25 minutes should apply to the situation with or without common data model. But operationally, there might be a difference. So some methods can be more easily applied if you have a common data model versus none. So to simplify things, we can talk about 4 sort of situations. The first one is that you have a common data model, and you also have a common protocol that each data partner would sort of implement. The other variants that you have a common data model, but you don't have a common protocol. So the other 2 situations are pretty self-explanatory. The fourth one is that you have neither. The first consideration is that if you want to create a common data model, you have to invest a lot upfront before you do any analysis. So this is an upfront investment that you have to sort of think about and whether it's worth it for your multi-center study. And the second is that if you have 10 databases or 10 sites, the programming effort that you need from each site. If you have a common data model, the goal of having a common data model is that since everyone's data look exactly the same after the conversion, you don't actually have to have everyone write their own program, because if I run my program and if it runs in my data source, it should run without any problem in other sources because everyone's data look the same, and that's the goal of having a common data model. So if you have a common data model, the statistical burden in each site is lower because you can have one site develop a program and the other side execute the program. And the ability to develop reusable tools is easier if you have a common data model because you know what the data looks like and everyone has the same common data model. And the ability to assess database heterogeneity, we mean treatment effect heterogeneity here. Every sort of variant shown here can do that. The ability to perform analysis tailored to each database. So if you rank it from best to worst, best is 1, worse is 4, you see a gradient here. So if you have nothing, meaning that everyone has complete freedom to do whatever they want, they can do the analysis the best tailored to the analysis. Common data models sort of restrict you in some way because in the end, everyone's data look the same and you want some sort of consistency. But that's not always the case. So that's why it can range from best to worst. And the ability to ensure consistent analysis across databases, having a common data model and having a common protocol is the best possible scenario because everything is sort of controlled by having this common model and protocols. Study-specific data management and cleaning. So this, again, is the upfront investment that you put into the common data model. So once you have the standardized common data model, which means that you do some sort of checking beforehand, when you do the next study, you will not have to spend as much time doing data management. So another way to think about this is that in terms of data cleaning or management, if you decide to have a common data model, the cost associated with data cleaning is the same whether or not you do one study or whether or not you do 100 studies. Because you spend the investment upfront, you do the data cleaning upfront. So it doesn't really matter how many studies you do. It can support one study or it can support 100 studies. The investment you put into is before you do any study. So in your multi-center study, if you only are going to do one study, maybe it's not worth doing the common data model because you actually have to spend a lot of time. But if you're thinking about a long-term collaboration and you are thinking about doing 50 or 100 studies, then maybe having a common data model will make sense. The speed of study-specific analysis, so we tend to think about this being the fastest because you can develop new tools or reusable tools and you have already cleaned and managed your data in some way, so the analysis should be faster. The marginal cost per study is lowest here, but it's cheating a little bit because the money is already spent in the upstream. So what it means is that you might have spent a lot of money upstream, but if you do 100 study later, the cost of each study is actually lower than you do 100 study and 100 of them are all one-off, meaning that you start over again every time you do a study. Reproducibility and validation across sites, we would think that a common data model and common protocol give you the best reproducibility. So this is just another way. So this is mostly personal opinions. You can disagree with what I just said here. So I shouldn't know how much time I have for Jeremy, but to end with some discussion. Again, we show these 4 domains, and this is something that we think about whenever we do a study. Again, this is not comprehensive, so if you try to do a repeated outcome analysis, time-varying confounding adjustment, marginal structure models, I would still think that you need patient-level data because it's almost impossible to do this type of analysis with summary-level information. But if your outcome is just one time, if your exposure is also sort of one time or in the sort of treated domain, it's possible to use summary-level information to do many of the analysis. So I think I will end here. So this is my content. I hope that you will get the slides. If you don't, contact me. I'm happy to share the slides with you. Thank you very much. Questions, comments, disagreement?
Just because we're in our region, I'd like to make one comment, if I may. Can you go back one slide, please, Darren? And thanks, that talk was great. So, unlike North America and Europe, we in the region don't have a common regulatory system. We all have different regulatory systems, which means that we all have very different medicines available. So even if we do studies on, for example, antipsychotics, what you'll find is we have 60 of them, and some countries have, Japan, I think, wasn't it, Kyoshi? You had 16 that none of the rest of us even had in our countries. And the other thing, of course, is we don't have the same dose. We don't have the same strengths registered and all of those things. So I think I'd add another column for those of us who are outside of the lovely regions that all sit under common regulatory frameworks around exposure kind of amount. Because, for example, if you were doing dabigatran we don't register the same strict product as you, and so exposure status is not yes, no at all the same way. Or if it was antipsychotics, would you beat the same ones, and those who we have to exclude lots because they're not available. So when you're not in a common regulatory system, there's another column here.
Yes, it's a good point. Thank you. Actually, there are many more columns that we could include, but this 16 by 9 ratio can only give you 4 columns at the most. But you can argue the same for outcomes. Like different databases might different ability to define outcomes. And for some of the covariates that you want to adjust for in your analysis. But I agree that exposure is probably one of the most important covariates in any given study.
I had another question for the do you put data from site-specific effect estimate? I mean, what if the effect estimate from the two different sets are not similar? Say maybe one HR is 1.7, the other HR is 0.7. Then what can I do if they are not similar?
So I have. So this is part of my FAQ. I get this question almost every time I have this type of presentation. My first answer is that this applies to every study or every type of analysis. So if you do individual level data analysis or if you do meta-analysis, you're going to have the same problem because treatment effect heterogeneity or heterogeneity by data source is intrinsic in the study. It does not depend on how you share data. So what another way to say this is that if there is a heterogeneity, if you see that in meta-analysis, you should see that in all other analysis that you do, because if you don't see that, that means you must have done something wrong, because the heterogeneity is just intrinsic to the data source. The second is that some people would argue that if there is treatment heterogeneity, you probably don't want to pool the data. Because this is from the more sort of RCT meta-analysis sort of mindset that if there is heterogeneity, you want to present the result sort of by trial or by data source. Although, also this is my third point, although I recently spoke to a biostatistician, so she sort of made an argument that if your study population is the people in these databases, that means you don't actually care about heterogeneity because this is your study population. So whatever you get is an overall effect estimate in this population. So the concept is pretty arbitrary. I mean, the concept of dividing people by data source is arbitrary. You can also argue that what if there is also heterogeneity by sex, by age, by medical history. I just didn't look for it. It doesn't mean that there is no heterogeneity. So this applies to every single database study that we do. So we just didn't look for heterogeneity and we just decided to pull all the data together, pretending that there's no heterogeneity by patient characteristic. The data source analysis is just a simple way or easy target for any multi-database analysis. We might be getting a little bit philosophical here, but the other argument is that it's okay if there's heterogeneity if your causal question or your research question or your study population is everyone in different databases. Then you have a strong argument to just pull the data together.
Thank you.
Do we have a break? No? Then it's my pleasure to introduce to you Dr. Jeremy Russell. Jeremy works for a company called Avion, but before Jeremy left Harvard to start Avion, he did a lot of work in propensity score and confounding adjustment in electronic healthcare databases.
What I'll be talking about is visualizing longitudinal study designs in healthcare databases. So there's a lot of pictures in this talk. And let's actually have a conversation. So maybe I'll ask a couple questions Maybe we can have a dialogue, as we're now at the end of the day. I'm a little tired. So as Darren mentioned, I'm an employee of and have an ownership stake in Any Incorporated. It's a technology company. This is a talk based on a paper developed by a number of people whose names you can see here, including Sebastian Schneeweiss and Shirley Wang, former colleagues of mine from the Women's Hospital and Harvard Medical School. So why are we talking about visualizing study designs? So I want to take one step back and say we're talking about visualizing study designs because of the way we want to communicate around studies that use real-world data. And so the ISPOR and ISPE joint task force created recommendations regarding good practices that enhance confidence in studies based on real-world data, or observational data, roughly speaking. And they recommended two key parts of this transparency communication. The first was about transparency in study execution, what did you do? And the other about transparency in process for the database studies, what did you plan to do? And if you look at the list of items about which one should be transparent, there's quite a number of them. But if you look very closely, there's design transparency, and one of the, in fact, the only listed here, item noted is a design diagram. And so just over the course of the afternoon here, you've seen a couple of design diagrams. I saw one in Dr. Platt's talk, I saw one or two in Dr. Toe's talk. And here I want to spend some time talking about a language for creating these design diagrams in a way that fully describes the study and all the various components. This is, as it says, a visual depiction that gives you clarity and definition. And why do we do this? For all the reasons that these design diagrams were so illustrative and important in the first two talks. They simplify review and communication, both for yourself and for your colleagues and for reviewers, but perhaps most importantly for decision makers, people taking the information from your study and using that to make a decision. They enable reproduction of your work in a way that's clear and easy for others to understand. They encourage systematic thinking about time-related aspects when designing studies or preparing manuscripts. In fact, just to bring it all together, I'll argue towards the end of the talk that it's pretty hard to have a mortal person time if you've diagrammed the study. You see it pretty clearly as you diagram this out. And last point, it eases identification of potential study errors. So this talk, as I said, is mostly in pictures, and the rest of the presentation will discuss creation of a study cohort from a healthcare database, a real-world data source, for use in a cohort study, case control study, self-controlled design, or other study design. I'm going to be honest and say that when I talk about studies, I'm mostly talking about cohort studies, so unless otherwise indicated, assume I'm referring to a cohort study. And it will show a method, and there are certainly others, but this will show a method for visualizing study designs that meet the criteria from the prior slide: easier communication, identification of errors, understanding, and ability to reproduce the study. So, starting. Each diagram that I'll show you has a timeline. And this diagram from the beginning is arranged in the order of calendar time. And what do we put on this calendar time diagram? you see at the top here some patient-level data as documented from a typical healthcare database. So you see on this diagram diagnoses and procedures, drug dispensings, laboratory tests, office visits, hospital stays, all the things that you would normally expect. And any given patient will have these items appearing on his or her own personal calendar time diagram. And for any given patient, we can now add what we can call first-order time anchors. And so first-order time anchors are represented as columns. You can see a column here indicating a particular date on that patient's timeline. And this first-order time anchor, meaning kind of most important time anchor, is in this case a cohort entry date. It's pretty fundamental for any type of study that we do. So what are first-order time anchors? Again, just the really fundamentals, redundant, I'm sorry, cohort entry date, outcome event date as examples. And we can then add to our diagram second-order time anchors. Second-order time anchors are things that are important, but perhaps less so fundamentally than the first-order time anchors. And these are typical concepts that you would apply as you design a cohort study or a cohort for a study. Things like a exposure washout window used to create a new user study in observational data. And these anchors are represented as boxes. And why are they represented as boxes? They're represented as boxes, meaning rectangles horizontally rather than specific points in time vertically, because they tend to cover a range of days. They may not always, but they tend to cover a range of time. So a washout window, for example, a typical study would say we required 365 days washout for the exposure and the referent to ensure that this was, or to have confidence that this was a new user of a drug. So what are some second-order time anchors that we tend to see? Washout window for the exposure, a washout window for the outcome, so no prior exposure, no prior outcome. Exclusion, variable exclusions, a window for covariate assessment, so as you characterize baseline covariates, a window for covariate assessment period, exposure assessment window, follow-up time. Again, these are all, generally speaking, longer than 1 day, so blocks of time that form our second-order study anchors. Okay, is everybody with me? So our diagram then begins to build itself. As you add criteria to your study, you add elements to this diagram. So starting with your first order, adding your second order. Do I have one more here? And in the end, you have what looks to be a fairly complete description of the design of your study. So here's, anybody want to tell me what kind of a study this looks like? This is the interactive part. So you have a cohort entry date preceded by an exposure and an outcome washout window, preceded by a covariate assessment window, and followed by a follow-up window. Anyway, so this would be, for me, a typical cohort study design. So you define your cohort entry date, you've made sure that nobody's had your outcome before, you made sure that people are new users, and then you follow people up over time. Does that make sense? Anyway, it's going to get harder. Now, one of the important things to notate here is, this is all, you can see that the washout window is maybe a little bit longer than the covariate assessment window, but we want to be more detailed about this. In particular, I think one of the most important things that we want to be detailed about is when we say no outcome, for example, 180 days prior to exposure, or a covariate assessment period. I'm going to start again. A covariate assessment period 180 days prior to the cohort entry date, right? Does that 180 days include the cohort entry date? Yes or no? Hard to tell by my description, right? But really, really different in terms of how the study is executed. I think it fell off the end of the slide here. But what you can see here is this notation to include bracketed numbers representing the time interval itself. And an open interval is denoted by square brackets and a closed interval by parentheses. So if the cohort entry date, sorry, it's the end of the day for me too. If the covariate assessment window includes that cohort entry date, you would say 180 to 0 with a closed bracket. If it doesn't, then you would use a parentheses. And I'm sorry, that fell off the end of the slide, so if you get a copy of the slides, that'll be on there. And that shows you, importantly, that important distinction. You can also see it. You can also see it here. Drawing the box over that cohort entry date would indicate including the date. And again, it's subtle, but it's an important distinction. So in this case, the covariate assessment window excludes the cohort entry date, but the follow-up window includes it. And to me, that would be an appropriate design. So let's do an example, and we'll do a number of these. I'm going to start with the standard text that you would read in the methods section of the paper. And this is a well-written methods section. It's very complete. What you often find as you read a number of papers is that many method sections are incomplete. But I'm going to give you all good examples of complete method sections. Can anybody looking at this tell me what the study design is? You have 3 seconds. 1, 2, 3. Can anybody tell me what the study design is? I can't. And this is why the diagrams are so useful. This large block of text is descriptive, certainly, but not perhaps illustrative as it could be. So I've taken the liberty here of highlighting some key parts of this. A simple cohort study investigated how well a combined comorbidity score predicted 1-year mortality. A uniform calendar time-based cohort entry date was assigned, and that was January 1st, 2005. Regardless of whether patients had a healthcare encounter on that date, patients were required to be 65 years or older when? Probably on the cohort entry date, right? But we're not totally certain. 65 years or older, and have no record of death in the year before the cohort entry date. It's a good exclusion. They were further required to have a recorded pharmacy dispensing between 365 and 485 days before the cohort entry date. So the cohort entry, I'm starting to build a picture in my mind, maybe you are too, but it's a little complicated, right? These requirements were designed to restrict the population to older patients who are likely to have been enrolled in the pharmacy benefits program over the study period. Risk factors in the 2 version of the comorbidity score were defined within 365 days before, but not including the cohort entry date. Additional baseline characteristics were measured over the same time frame. That's an important phrase as well. Patients were followed for the outcome for 1 year following the cohort entry date. So, I think I got it. Right? But it's a little hazy. So let's do this the other way. Cohort entry date was assigned January 1, 2005. So that's our first order time anchor. patients were required to be 65 years or older before the cohort entry date. Now, that wasn't explicitly stated, if I remember correctly, in the text, but we'll assume a little bit here. So we have an exclusion criterion, which is age less than or equal to 65, assessed on exactly the cohort entry date. So we'll use numbers that index in time from the cohort entry date. We'll call the cohort entry date 0. And so we'll say here that this exclusion of age less than 65 is measured on days 0 to 0 with closed brackets, meaning on day 0. Good? And you can see how that blue bar there crosses over the cohort entry date. We also require that patients have a recorded pharmacy dispensing between 365 and 485 days before the cohort entry date. That to me was the one that was a little bit hard to picture, but once you see it, it's kind of hanging out there way before. And have no record of death in the year prior. So we're starting to build a picture of what this study looks like. Risk factors in the two versions of the comorbidity score were defined within 365 days before, but not including the cohort entry date. So now that's our covariate assessment window for building that risk score. And you can see that it does not include the cohort entry date. That's very clearly pictured. And patients were followed for the outcome for 1 year following the cohort entry date. The text wasn't very clear, to be honest, about whether that period included the cohort entry date or not, but we'll make the assumption that it does. And so you can see now that that's days 0 to 365 inclusive, and we now have a full picture of this study. Just show of hands. Is this clearer than the text? Yes? No? No opinion. Everyone should have voted. Let's do it again. Yes? No? No opinion. All right. We got about 50%, so 50% abstention. So you can see how we can start to understand this study better. Let's do this again. I won't read it all this time, but you can see the key phrases in this study here. This is a study by, I don't know, some author, I don't know, I think his name is Toe. Core study investigated whether ACE inhibitors different from ARBs with respect to risk of angioedema. Do you want to read this for us, Dr. Toe? The inclusion criterion was initiation of a study drug after 183 days or more without dispensations for either of the drug groups being compared. Anyway, let's start to build this out visually. The cohort entry date was the first prescription for an ACE or ARB. Patients were excluded. They had intermittent medical and drug coverage in the 183 days before, but not including the CED. You can see how the diagram is a little more, it's clear in what exactly that means. The washout for incident exposure and outcome was 183 days before, but not including the cohort entry date. Patients were excluded if they were under 18, or if they initiated both ACE and ARB on the cohort entry date. It's a really good exclusion that you often don't see notated, but it's a pretty key one. What if you start both drugs on the same day? Covariate assessment window was 183 days before, but not including the cohort entry date itself. And follow-up began on the cohort entry date and continued until the outcome of interest, switching discontinuation, death, disenrollment, 365 days, or the end of the study period, whichever came first. So, if you look at this diagram, and we've looked at a couple of these now, does this make sense? Just without thinking too hard about it, what kind of study is this? Darren? What kind of study? Darren thinks it's a new user cohort study, and since he was the first author, we're going to trust it. And it's pretty clear, right? It's pretty clear that a whole bunch of stuff is happening before the code entry date, and one thing is happening after, and what's that thing happening after? That's the follow-up. This feels consistent and right to me. You can agree or disagree. Let's take a variation. This is first authored by a guy I used to work with named Josh Gagne. Many of you probably know. In contrast to the previous study, which defined the code entry date before applying exclusion criteria, a similar study investigating ACE versus ARB and the risk of angioedema identified every new episode of treatment initiation within the study period and then picked only the first new initiation episode for each patient after the exclusion criteria were applied. So if we take that and we diagram it, it's a little bit small, but it's on the right, and we compare it to the one from the first iteration, which is on the left, we can pretty easily visually compare these two and see that there's one extra thing on the right. And what is that thing? It's in light blue. It's an exclusion criterion. What exclusion criterion is it? I'll read it because it's probably a little hard to read. Keep first qualifying new initiator episode observed within the study period for each patient. So now it's very clear that we've added an additional criterion to the prior study, and now we have two substantively different analyses that we're doing. And not a criticism in any way, but just these kind of subtleties are hard, in my opinion, to pick up from large blocks of text. Okay, let's switch gears a little bit. We're going to start making the studies a little bit more complicated, or a little bit more, perhaps add some more subtleties to the study. So this is an exposure-based cohort entry, and the study is restricted to adherent users. Can anybody kind of picture what that would mean, or want to read the text and picture what that would mean? Cohort study investigated whether statins differ from glaucoma agents with respect to mortality. I'm just going to read the key part here. It says, did I highlight this? I did. Non-adherent patients were excluded, where non-adherence was defined as patients with less than 3 dispensings for statin or glaucoma therapy within 180 days. And where's the follow-up began on the date of the third refill and continued until outcome, death, disenrollment, or the end of the study period. So we're only going to include patients in the study if they had 3 or more dispensings for statin or glaucoma therapy, and we're going to begin follow-up at the time of that third dispensing. Does that make sense? Okay, now what would happen if we began follow-up immediately? Somebody. So if we didn't wait to begin follow-up till after the third dispensing, what would we have? There's a theme here. That would be a mortal person. So here we can very easily see the difference, okay? So we have some standard stuff. We have a washout window, no exposure to statins or glaucoma drugs. We have exclusions, intermittent medical and drug coverage, baseline conditions, so on and so forth. We have an exposure assessment window. This was new, I think, on this one. Meaning we're going to spend 180 days looking to see whether that patient had those 3 or more dispensings. We're going to apply some other exclusions, cardiovascular conditions, age exclusion, measure covariates. But look, we're only going to start follow-up after that third refill. And so you can see that there's this vertical line here and it's clear that you're not following up during the time that you're assessing exposure. And so this gives us a very clear picture of how this study works. It's not a complicated study, but it's not the easiest study either, right? And also a very clear understanding that we're not introducing mortal person time by following up while we're still busy checking to see whether the patient had 3 exposures. So it hits at least 2 of our criteria before about checking for errors and being clear about the intent of the study. Okay. Let's talk about nested case control studies with risk set sampling. Again, there's a lot of text here. Let's just look at the picture and see if we can understand what this study is. So, let's just take a second. Everyone look at the picture. Is it large enough for people in the back to see? I have some glasses in the bag if anyone needs them. So what's a substantive difference here between this picture and some of the earlier pictures? I heard some murmuring over here. Anybody want to shout? So, there's 2 gray bars. The first one is our usual gray bar that we've had. What's that second gray bar? Someone over here. The second gray bar is event date. And we said the gray bars are our first order anchors. First order anchors are particularly important. So I've said that the cohort entry date is particularly important, and the event date is particularly important. So I think already without even knowing what I'm looking at, I've noticed that there's an important difference, and this is hinting to me that this is some sort of case control design because we're looking at an event date, perhaps looking back in time to a cohort entry date. And for me, I love case control designs, but I feel like case control designs are easy to introduce errors into if you're looking at, say, exclusion criteria during this time. And you see a lot of studies, unfortunately, that look at exclusion criteria during this time. So I think if we look at the study, we can see something that makes a lot of sense. So we have a washout window, no oral or anti-diabetic agent. We have an exclusion assessment window looking for history of bladder cancer. We have an exclusion for patients without the required amount of history. We have an exclusion for patients less than age 40 or who have insulin. We have assessment of covariates. And then we have a follow-up window looking at a particular event date. And we assess covariates on that event date. So this gives me a pretty good sense of this design, right? So, and if we go back and read the text, let's go back and read the text and see if it makes sense to us. The cohort entry date was the first initiation of anti-diabetic agent. Does that make sense from the diagram? So, would you have said that this was a cohort entry date about an anti-diabetic agent? Washout window that included all available data before the cohort entry date. So days, negative infinity to -1, so all available data. Patients were required to be enrolled in the primary care database with at least a year. I got that from the diagram. They were excluded if the first anti-diabetic agent prescribed was insulin. So remember that was there. What was this exclusion year for age less than 40 or prescribed insulin? they didn't have the medical history for at least 3 years. Or if the patient had a history of bladder cancer. Cover rate assessment period included all available data before the cohort entry date. Follow-up started on the cohort entry date and continued until censoring. The date of incident bladder cancer was the outcome date, and only cases with at least 1 year of follow-up between the cohort entry date were included. And you can see that matched controls were sampled. And so I think this gives a pretty good sense of the design here. It also gives you a good sense of how the exposure was assessed. Going back to the first talk, this is Ever, Io, or Rosie as the exposure. Does this make sense? Again, these designs are getting a little more complicated each time, but I think that the key criteria are pretty well. So, self-controlled design. This is an outcome-indexed self-controlled design. So you guys all know what case crossover studies are. Think about it for a sec. And reconcile your understanding of a case crossover study with a diagram. What would you expect to see for a case crossover study? So, you can see here 2 exposure assessment windows at 2 different times. Be your contrast with 1 event date. So, event date, sorry, it'll be the end of the talk and I'll finally learn how to use this. Yeah, so the question is, do you always put them in columns rather than longitudinal? I do, and that's for 2 reasons. One is it gives you a sense of the order in which these criteria are applied, which can be very materially different if you do them in different orders. So if you apply, for example, an exclusion assessment window before a washout window, as opposed to the reverse, you can get a different set of patients. The other reason that they're in columns is that a lot of these things are occurring concurrently. So the columns, is that the question you're asking? Yeah. So the stack gives you a sense of how these things are concurrent or not, which I find very useful. So as you read down, you see the order, and as you look across, you see which of these are overlapping and which of them are not. The last 3. Exposure assessment window, washout window, and exposure. So I read this down as you have an event date, which is your MI. This is a case crossover study. You excluded anybody who had a prior outcome. You excluded anybody who didn't have the history. And you exclude anybody age less than 75. Okay, at that point you're allowed to be included in the study with an event. And you look at your event and you assess exposure in the 10 days prior. And then you have a little bit of another washout, and then you contrast to another time, which is farther in the past. And that creates your contrasting time. And for me, it kind of reads logically. Does it read logically to you as well? Okay. How about to others? Does this read logically for a case crossover? To me, it does. And we can talk about whether it reads more logically than the text. But I think especially as you use designs that maybe are a little bit less frequently used, the picture I think really helps explain what the study is doing. I think this is the last one. Exposure indexed self-control design. So does anybody have a sense of what this diagram might look like? So you have a cohort entry date, which is in this case a vaccination. follow up here, follow up here, with the appropriate washouts and exclusions applied, and allows you to create that contrast among patients with an outcome. Does that make sense? Does anybody take issue? All right. So that's it. That's it for this range of diagrams here. I put in a couple examples of errors, and we've talked about most of these at this point. But I want to show you how easy it is to find errors. Should there be errors? Does this look like it has a problem? Or way back to the very simple diagrams now? Anybody see a problem? Raise your hand if you see a problem. I see no problem. But now, it's hard to identify, it's hard to give an exact case here, but sometimes you see studies where covariates start to be measured into the follow-up time. I see this with, I'm trying to think, there was a RA study that I read a long time ago that measured steroid use during the follow-up time. And, it's subtle in the text, but it's really, really, really loud and obvious when you print it like this. And the right thing to do would be, something Darren likes to do would be accounting for time-varying covariates. But if you don't do that, then it's very clearly a design issue, and that becomes an introduction of an intermediate without control for it. Another example. Anybody see a problem? Does this look right or wrong? Again, a little simplistic, but does anybody see an obvious error here? Someone in the back, I think. I saw movement in the back. Yeah, so looking at exposure at the same time you're looking at follow-up, to me, at least raises the question of whether this was done correctly or an error, and this is, I'd say, a simple form of a mobile person time. Does that ring true? So you can see how errors that are a little bit subtle in text become very easily identified. And one last point. Talk about sensitivity analyses. I'm going to go back to prior. We can look at this diagram and we can see, 7 or 8 different criteria that we've used to build this study, or sort of parameters that we've used to build this study. And one of the things that makes a lot of sense to do very frequently is to apply sensitivity analyses to understand if I shorten my washout window or I lengthen my washout window, if I extend follow-up time, how does this change the effect estimate that I receive? So I'd say that one of the other nice things about these diagrams, it gives you all the options of places that you may want to apply sensitivity analyses. And it may not make sense to apply them everywhere, or even anywhere, but it at least lets you see where you might vary your assumptions, which variations in assumptions make sense, and which don't. So, extending an exposure assessment window into follow-up time, that's not a variation that would make sense. But extending follow-up time from 1 year to 2 to 5 very well might make sense. And so I think the theme that you're hearing throughout this is, first of all, simplicity. These are easy to understand once you've constructed it. And number 2, support of good practice as we do our research with observational or real-world data. And so sensitivity analyses, I'd say, is an example of good practice. And it gives us a real sense of where we can make a change that might be meaningful, and where we wouldn't. The other thing I'd say about sensitivity analyses is that it's important to do sensitivity analyses that are kind of internally consistent with all the other things that you're doing in the study. So if you lengthen a covariate assessment window, but you don't lengthen your washout window at the same time, are you doing something that makes sense? Maybe, but maybe not. And being able to see the internal consistency of the design, even if it's not an error, but it's maybe just a poor choice, is another thing that these visualizations get us. So that takes us to the end. And I will be happy to entertain any questions. We have a couple minutes left. We have a question in the front. We have a microphone on its way.
This is more of a comment than a question, or an observation than a question. So we do a journal club every 2 weeks where we take a recent paper from the pharmacoepi literature and we talk about what they did and whether we think it made sense or not. And it takes, usually out of the hour that we spend on the paper, about 50 minutes is spent trying to figure out what they did. And if everybody did this, it would put our journal club out of business because we would know what they did right at the beginning. But I think this would be really helpful in terms of describing what happens in the study. And I think you're right that the text leaves enough, on average, the text leaves enough ambiguities that you couldn't recreate one of these diagrams just from the text in the method section. And then the second point, and this relates back to Darren's talk as well, is you spent a lot of time focusing on whether cohort entry date is included in the period prior to the cohort follow-up or in the follow-up time. And even within our distributed network, where we try to have the same protocol done at every site, we occasionally find that gets screwed up just because of ambiguities in the writing. So the more that we can clarify that stuff early on, the better.
Comes as no surprise that I agree on both points. To your first point, Journal Club. I think there's a generalization here, which is true, which is that one of the motivations at the beginning was using these diagrams to explain our work. And I think if we use these in Journal Club, I think we would get to the heart of the discussion 50 minutes faster, maybe 45 minutes faster than kind of the usual. I think it also helps particularly in Journal Club because, I don't know, at least in the Journal Clubs I've attended, not everybody reads the paper. So it's a quick way of getting to the key points. But I think, the general point, this is a great way of explaining our work to people who may not put in the same amount of time and effort in understanding our work that we put in creating the work. And I think one of our greatest challenges as scientists is being clear and having other people understand what we've done and creating that environment where people will accept the results and the meaningful work that we've created. And I think this is a way of easing that for our reading audiences, and that does them a favor. I think it's also good for the work that we do as well. The other response I had, lost. In all of these cases, I was able to create a diagram because the text was relatively complete. Maybe not perfectly complete, but relatively complete. Not depicted here, not coincidentally, are the cases where I could not create a diagram because very frequently the text just has large holes in it. And most of the journal clubs I've gone to where we spend the full, 59 or 59 and a half minutes talking about the design of the paper, it's because we had to impute or infer some part of it that wasn't either clearly stated or stated at all. And I think these diagrams, if an author goes through the trouble of making this diagram, they'll also really help readers understand the completeness of the study, because I think very, very, very frequently work is not reproducible or not understandable because it's not well described. And that's word limits in journals. It's perhaps some sort of authorship issue, but really it's up to us to really explain our studies very, very clearly. And if a picture is worth 1,000 words, I don't know if that's a saying that translates. A 3,500 word limit